Charles, we are really grateful of having you here. Please feel free to share your screen, and you can talk of learning health systems, mobilizing computable biomedical knowledge, and imperative for learning health systems.
Thank you very much, Daniel. Can you hear me and can you see my screen?
Yes, definitely. We can hear you and your screen.
Okay, I apologize for not being able to speak to you in Spanish. That is a goal of mine, to learn to speak Spanish, but I haven't quite achieved that goal yet. It's a privilege for me to be here, and I wish I could be there in Argentina with you for many, many reasons. I need to disclose that I serve on the board of directors for a nonprofit organization promoting learning health systems. So today I'm going to take you through a journey that has 6 parts. First, I'm going to talk about knowledge. Then I will talk about learning health systems. Then I will tie these 2 ideas together by introducing the concept of computable biomedical knowledge, and go on to say why this is an essential ingredient in a learning health system to enable what I'm going to call mass action. If time allows, I will take you through a quick example focused on clinical pharmacogenomics, and then I will even more quickly talk about a global movement to mobilize computable biomedical knowledge and invite you all to join this movement. So to begin, I want to offer you a way to think about knowledge, and that is, in very informatics terms, to think about knowledge as a result. And this result could be the result of an analytical process, or it could be the result of a deliberative process, or it could be both. But knowledge, I'm arguing, is the result of an analytical and/or deliberative process that holds significance for an identified community. In other words, for a result to become knowledge, some organization has to say, this is significant to us, we endorse this as knowledge. So examples of biomedical knowledge, viewing knowledge in this sense as a result, could be seen on this slide. The ones on the top, the examples on the top, are primarily analytical in origin. They originate from analyses, and the ones toward the bottom are primarily deliberative in origin. They originate from discussions and deliberations. So examples are predictive models, computable phenotypes, propositional networks, best practice guidelines, decision trees, and finally policies, which are the best example of knowledge that result from deliberative origins. So that is a brief introduction to the topic of knowledge. Now moving on to learning health systems. I don't know how many of you are familiar with the concept of learning health systems, but the fundamental activity that learning health systems carry out, and the most important aspect of what a learning health system is from the viewpoint of this presentation, is this notion of learning health systems as carriers of these continuous cycles of study and change leading to improvement. So within a learning health system, this cyclical process of study and change leading to improvement begins with formation of a learning community. And this learning community forms around some significant health problem of interest against which the community wishes to improve. This could be lowering morbidity and mortality. This could be increasing access to care. It could be any health problem whatsoever that a community takes interest in. The cycle begins when this community begins to capture practice as data. What are we doing now? And moreover, what are the indices against which, what are the metrics against which we would like to improve? The community then assembles data that reflective of this practice in a form that is amenable to analysis. It analyzes the data and creates a result and creates something that could be seen as knowledge. This knowledge created locally by the community is combined with external evidence from papers and other sources, because it is very likely that this health problem, which is significant, has also been studied by others, and those studies have generated evidence which can be merged with the evidence that the community itself generates. This combination of evidence, this combination of knowledge is then interpreted, and the community decides whether enough has been learned to design an intervention that would be intended to create improvement against the problem of interest. The intervention could be a single intervention, or it could be 2 or 3 alternative interventions, which would create a kind of implementation experiment. It could be done either way. The intervention would then be implemented, or interventions would be implemented, action would be taken, and this would bring the cycle around to the beginning of the second iteration, where current practice, now that the system has changed, would be captured as data. The metrics, which would be indicative of improvement or otherwise, would be measured. The new practice, the changes, would be related to any improvements, and those data would be assembled and analyzed, and that would create a second cycle. And the cycle would repeat with the hope that over successive iterations of the cycle, improvement relative to the problem of interest would occur. And this is the fundamental activity that learning health systems undertake. So the takeaway from what I just said is that in the view of learning health systems, better health requires these complete cycles of performance to data, P to D, data to knowledge, D to K, and knowledge to performance, K to P, and back to P to D. This contrasts with what most of us who are academics were taught to do. What we were taught to do was take data, analyze it, create new knowledge with the result, and publish it in a journal. Now, we do this with the hope that there is someone who is going to read that journal article and take the knowledge there to practice. But too often that isn't the case. And too often what we who have been trained to be good academics do is then go on and collect new data, take that data to knowledge, and publish another paper. Again, hoping that there is someone here to take that new knowledge and put it into practice. But too often that isn't the case. And these complete cycles are also certainly not this, which, as you can see, is a gap at the top of the cycle. And this is very, very important to what I'm about to present, where one group, and this is certainly the case in many medical centers in the US, is the health services research group. And this group is engaged with taking data to knowledge and generating results. But there's a completely different group, often called the quality improvement group, which is completely different people, and it's their job to take this knowledge and put it into practice. But because these are two completely different groups of people with different cultures and different leaderships, there is a gap here, and very often it is not possible to jump across this gap, complete the cycle, and go from data to knowledge to performance. So that very quick introduction to learning health systems takes us to the concept of computable biomedical knowledge. So what we can see is that there are two complementary ways to represent knowledge. And this is key to the main point I am going to make in this talk, that we can represent knowledge in human readable form, and we are all very accustomed to this, with knowledge represented in words, pictures, and equations in such things as journal articles, and what we do is we read these articles. But there is also a complementary way of representing knowledge in computable, machine-executable forms. In other words, in code that computers can understand. So the premise of my talk really is the importance of these two complementary ways to represent knowledge. So just to show the relationship, here's an example of human readable knowledge in a paper that is published in a prestigious peer-reviewed journal. And within this paper, there is new knowledge, a result, and in this case, the result is expressed in a predictive model in a logistic regression equation. These are all very familiar things to us. But that same knowledge can be made computable by representing it as code. And this code could be code that takes in the characteristics of the person and computes a risk score for that person. And we call this computable representation of the knowledge a knowledge object. And as you can see, at the core of this knowledge object is code expressed, as you all know, at its root as ones and zeros. So this idea of going from human readable knowledge to computable knowledge can be seen as extending the publication pipeline. What we have now is, and in an almost ubiquitous form, is human readable knowledge that is stored in libraries. What I am advocating for is the idea of taking this human readable knowledge and routinely extracting from it a model which can be encoded, and through programming represent in functional code that same knowledge in computable form. And if we think somewhat about the future where this would be done routinely, libraries of the future would not only store human readable knowledge, but would also store computable knowledge as well. So we've now introduced the concept of knowledge. We've introduced the concept of learning health systems as executing complete cycles leading to improvement and the danger that might occur, particularly if there is a gap between the creation of new knowledge and the application of that knowledge to practice. And we've introduced the concept of computable biomedical knowledge as a complement to the human readable knowledge we are all accustomed to. Now we're going to connect those concepts and discuss why computable knowledge is an essential learning health system ingredient to enable what we will call mass action. So you can think about knowledge, which is the result of the data to knowledge process, as the keystone that holds this learning cycle together. It enables the bridging of that gap between data to knowledge and knowledge to practice. And just as a keystone supports an arch at the very, very top and holds that arch together, so does knowledge as the keystone of a learning cycle, which holds the cycle together and enables it to be continuous. Human readable knowledge by itself fails to hold the cycle together. And as I've described, if we have this gap between data to knowledge and knowledge to practice, and what we have at this point where we need to jump this gap is only human readable knowledge, we need to ask ourselves, how does a paper that offers a useful prediction model, for example, with no infrastructure to manage or deploy that model, create changed practice? That's why it is often very hard to get across that gap. And this is why we very often see a situation where there can be a great time latency, a great time period that elapses before new knowledge, which might in fact be very, very helpful to improve health and or improve care, a 17-year gap between the discovery of that new knowledge and its implementation in practice. There is nothing to close this gap. There is no keystone to make this cycle continuous. I would submit to you that learning health systems and more generally the world, to be modest, need computable biomedical knowledge to jump this gap. And we're going to represent computable biomedical knowledge, not by one, but actually by a combination of these knowledge objects for reasons that I will get into in just a moment. So computable biomedical knowledge, I would submit to you, is needed to routinely jump across this gap and make these learning cycles continuous. Now, to see why this is the case, we need to look at the difference between so-called discovery systems, this data to knowledge to journals, for which human readable knowledge has actually served us pretty well for many, many centuries. And as we will see, learning systems which require a complete cycle. What we see with discovery systems is they require only mass access to knowledge. Learning systems, by contrast, which close this cycle and do it routinely, require mass access, mass action, in contrast to mass access in the modern world, to persist knowledge that changes rapidly and deliver advice from it at large scale. And to do this, to put learning systems to work to engender widespread and general improvement in health, requires computable knowledge. Back to discovery systems for a moment and why they require only mass access to knowledge. You can think about the way in which research is done as a serial process where somebody takes data to knowledge, publishes that knowledge in a journal. Somebody else reads that journal article, but that other person is also a researcher who is primarily interested in creating new knowledge. So that person learns from the first published article and does his or her own study, which generates another journal article. Similarly, another researcher might read that first article and use it to inform his or her own research, which takes data to knowledge and creates another journal article. This is what I call mass access, and this works very, very well as long as the primary thing you are interested in doing is generating new knowledge that will end up in a journal, and not necessarily making sure that that knowledge in that journal translates into implementation and improved health, which is the goal of learning health systems. Now, learning health systems are dynamic and potentially large scale and require mass action. And I'm going to submit to you that to enable mass action, computable knowledge is essential. And we can think about mass action in a couple of ways. One is that if you want to implement change, if you want to implement the behavior of people, whether they are healthcare providers or patients or administrators or anyone else in the health ecosystem, what you want to do through the implementation of this knowledge to practice or knowledge to performance part of the learning cycle is provide them with information. And you want to be able to do that at a large scale, reaching in principle an infinite number of people, and provide them with information that is tailored to their particular needs. By virtue of seeing these different colors, we're recognizing that each of these people might have different needs for information of different types, which can be computed out of these knowledge objects. And then these people will take action based on the information they receive, and that action will complete the cycle. So that is one aspect of mass action requiring computable knowledge. A second aspect is the fact that increasingly in the modern world, the knowledge we are using to inform behavior change, to improve health, is dynamic. Our knowledge base is changing very quickly. So we need a far, far better way than journal articles can provide to update the knowledge we use. So what we can see here, however, is if the knowledge is in computable form and is represented as knowledge objects, new knowledge can be added as it is generated. And as you see with one of these knowledge objects changing color, a particular piece of knowledge can be modified as, for example, more data are provided to update some kind of predictive model or algorithm. And new knowledge can also be added. And then just as easily, in a very agile way, the same mass action script can be executed, whereby now different and enhanced messages with its enhanced knowledge base can be sent to these recipients and action taken on that basis. And this is the essence of what I see as mass action, dynamic knowledge distributed on a large scale, almost simultaneously, to engender widespread health improvement and behavior change. We have built at Michigan an infrastructure we call the Knowledge Grid, and you can learn more about the Knowledge Grid at its website, kgrid.org, which is infrastructure that enables, I'll just go back for a second, this kind of mass action to be implemented in a routine fashion. And this infrastructure of the Knowledge Grid encompasses several components. First of all, the ability to create knowledge objects. Second, the ability to store them in a specialized digital library. Third is what we call an activator to generate the advice that would go out to decision makers. And then finally, interfaces, APIs, which can allow the delivery of these messages through existing health information technologies such as e-health apps and electronic health records. So just to illustrate this a bit and show you how it might work in practice, we have taken great interest in clinical pharmacogenetics, and particularly the knowledge that has been assembled by the Clinical Pharmacogenetics Implementation Consortium in the US called CPIC. Well, turns out this is what the CPIC recommendations look like now. This is the knowledge that has been generated, and as you can see, it is represented in human readable form. You can't compute on this. But what you can do in a way that is very much analogous to the pipeline I showed you before of taking human readable knowledge to computable knowledge, you can take this table, convert it to a form that is much more amenable to coding by virtue of its structure, which takes a genotype to a phenotype to dosing advice, and that's the structure of the pharmacogenetics knowledge created by the CPIC. And you can do this for specific drugs and drug-gene relationships. You can employ a programmer who can represent this table, and this is not particularly difficult programming, as machine-executable code in a knowledge object. And in this case, a knowledge object would take in the genotype of a patient, combine it with the relationships between dosing and other characteristics and the patient's genotype to generate recommendations. So I would argue, coming back to this mass access and mass action distinction, that in the current state, CPIC's guidelines, as I showed you, are currently in human readable form in tables. But in a future state, and we have not completed this work, although we have encoded all of the current CPIC guidelines as knowledge objects, this future state would require 4 steps: that these guidelines be in fully computable form as knowledge objects. This we have done. Making these computable objects publicly available so anyone could use them in a trusted digital library. The deployment of activation services that would take in genotypic characteristics of individual patients, combine this with the knowledge that the CPIC has generated to generate advice about dosing and other therapeutic strategies that would benefit the patient, and then the delivery of advice through apps or EHRs, and this would enable mass action and take us from mass access dependent on humans reading the human readable knowledge from these tables to mass action, which would make this computable on a large scale and moreover enable agile change in the knowledge base as the CPIC continues its research and discovers new important knowledge and relevant relationships. So to bring my talk to a close about mobilizing computable biomedical knowledge and its importance, I'll just acquaint you with a movement which we have started in the US called MCBK, Mobilizing Computable Biomedical Knowledge. We started this in 2017, and we have had annual meetings in the US beginning in 2018. Our virtual 2020 meeting attracted 240 participants. I'm thrilled that the movement is now beginning to go global. A group in the UK inaugurated an MCBK meeting in October of 2019, and the MCBK movement in the UK is now well underway. It has acquired funding and may in fact surpass our US work very, very quickly. We'd be very interested, if any of you are interested, in forming a Latin American chapter of MCBK, and I hope I stimulated your interest in this. The US work on MCBK is working through 4 work groups, producing key deliverables. We expect to issue a metadata standard for these digital knowledge objects very, very soon. Everything we are doing is open and available at this website. And if you would like to join MCBK, if you send email to this address, we would be happy to add you to our mailing list. So this completes my comments. I would welcome any questions that you might have. Thank you very much. It really was a pleasure to speak with you today.
Well, Chuck, I was late, but I'm here.
Nice hi, Paula. To see you. Nice to see you. Good. I'm well. Thank you.
I guess you must be really excited because it's one day away from election day.
We're scared.
Bueno, no, lo estoy saludando a Chuck porque ha venido varias veces y es un amigo de la casa, and I wanted to thank publicly that you were a great asset in our project. You helped us a lot in developing a whole lot of ideas, and when you visited us, it was really you gave us a lot of insight that was really good for us. So just want to say hi and thank you for always being available when we need to have you at our annual meeting.
Thank you, Paul.
Okay, Charles, we have some people asking for your contact details. You showed it in your slides, and Paula also has written it in the chat box. So I think there will be many people interested in joining your efforts for a learning health system network, hopefully joining efforts from different parts of the world, at least from Latin America also. That is our main focus in this conference. I know you have been very kind and you have a lot of commitment with this effort we are making with this conference, and you elected to give it online, not as a recorded presentation. So I want to thank you very much for your presentation. It was very interesting. We have been following your work, of course, since a long time. But I think it's really great to have many people here in the Zoom meeting room, listening to your words and engaging with the idea of a growing learning health system.
Thank you.
¿Y hay alguna pregunta del auditorio en castellano que quieran que le traduzcamos al profesor Friedman? que quieran escribir en el chat y tanto Paula o yo se la podemos traducir. I'm asking if there are any questions, at least in Spanish, and then we can translate it to you.
Oh, I'm proud of myself. I think I can translate the question that's in the chat. I think the question is to explain a bit more about what is meant by mass action.
That's it.
Okay, good. I'm learning. Yes, I realize mass action is a somewhat abstract concept, and I realize I went through this very, very quickly. So let me elaborate. You can think about mass action as having two components. The major aspect of mass action is this idea of being able to get personalized advice or personalized information to a virtually infinite number of recipients very, very quickly, so they can take action to that is beneficial to health, whether it's if they are patients, action beneficial to their own health, or if they are care providers, beneficial to the health of their patients. So you can think of this as massively parallel decision support in a way. This requires infrastructure, and I did not have time to dwell on the infrastructure required to build this in any kind of detail, but that's what we have done with the knowledge grid. The knowledge grid can take information about a particular individual, operate on that information with knowledge objects, generate advice. Then it can take information about another individual, operate on that with knowledge objects to generate advice. But what I'm describing to you as sequential would actually happen almost simultaneously. So a mass action system of the type I'm describing could be constantly taking in information about individuals, applying knowledge objects to them, and generating advice specific to that individual. That's what I meant by the arrows coming in and the arrows going out. Now, that's only half of the mass action story. The mass action story second part has to do with the fact that knowledge is becoming increasingly dynamic and large in magnitude. Algorithms, models are being developed faster than we can keep track of them. So we need to manage these models, and we need to be able to assemble them in combinations because, for example, a panel of predictive models may, if applied all at once, might enable better decisions than these models applied one by one. So if you assemble knowledge objects, each one of which offers a prediction, and assemble them as a set, that creates a much more powerful kind of information than would be available from applying these knowledge objects one by one. So this is a second kind of mass action, being able to assemble and reassemble these knowledge objects, and also to change them very, very quickly as these models are updated. I hope that additional detail about what mass action is helpful. Learning health systems will not be able to improve health at scale without infrastructure that supports mass action, and computable knowledge is essential to make that mass action happen. I hope that was helpful. The second question, I will need translated for me. I don't want to guess.
If you have more time for one more question.
I do.
Which were the first initiatives that this group took?
The MCBK group, I assume. is what is being referred to. Well, the first thing we did, to be very honest, is try to form a community and establish that there was enough common interest around this idea of computable biomedical knowledge to start a movement. So actually our first meeting was more of a organizational and introductory meeting to generate some understanding about what this idea was about, and to see if there was enough interest to push forward from there. And we quickly discovered that there was. We then formed 4 working groups. One focused on standards, and that group has been working on the very important problem of creating metadata standards for computable knowledge objects. And you very, very quickly can see that if a knowledge object at its core is code, you have to put metadata around it so people know what it does, so people know where it came from, so people know who owns it, so people know how to access it, and most important of all, so people can trust it and put it to use in their own organizations. So one of our work groups has been working now for close to 2 years on the development of metadata standards, and a first set of those is about to be forthcoming. Another one of our groups is focused on technical infrastructure, and that group is articulating in more general terms what a technical infrastructure supporting computable biomedical knowledge must comprise. The knowledge grid that I described to you is one example of a technical infrastructure, but there are many, many different ways to do this, and the technical infrastructure group is coming up with a general model for the infrastructure needed to support computable biomedical knowledge. There is a group working on trust, and this group is related to the standards group, but is focused on exactly what potential adopters of computable knowledge in their own mass action environments need to know about that computable knowledge in order to sufficiently trust it. And they are getting into the very, very important issues of, for example, understanding and establishing whether there is bias in this knowledge or not. And finally, the fourth group is focused on outreach and sustainability, and is forging very important connections between the MCBK movement and other groups, for example, the Logica group and HL7 and Health Data Research UK and NICE in the UK and other organizations that are pursuing in their own ways related efforts and related goals. So I think our initial initiatives have been focused along those 4 lines.